afternoon. My name is Justin Cummings. I am a fourth year electrical engineering student here at Alfred State. Along with my group members, we would like to introduce our senior project named the Motion Detection Car Security System. And just a quick overview about the topics we'll be talking about today will be the main part of the circuit, which is the PIR sensor, some of the assembly, a little bit of the troubleshooting we went through, some of the references that we used to build this project, just to name a few. So what is it? This project is intended to promote motor vehicle safety due to the increase in car break-ins and car collisions while stationary or operating a motor vehicle. Especially in like city areas or even in a setting like this on a college campus, you see a lot of traffic, and your car it can be put in harm's way. So it'd be very nice to have a set of eyes while you're away from your car to see what's happening. So car accidents can happen to drivers anywhere at any time, as we know. Normally in the busy holiday seasons, packed parking lots and more frequent shopping trips mean an increase in fender benders and car accidents. This is where our project would come in handy. If someone backed into your car or walked on the side of it with the shopping cart or anything that happened to the outside of your car, photos will be taken, which will include the damage to the other's car or who did it, and your car. Their license plate will be shown and other views of the car. This data will be very helpful in identifying who is responsible, and this can be put forth to file an insurance claim, carried to the authorities, or whatever other legal uses you may have. Like my partners Lenford and Ryan would love to say about this project, you can think about it as your car's personal bodyguard. So the motion detection car security system monitors your parked vehicle 24 hours per day. Whenever it captures a picture, it will record the date and time along with a high quality photograph. The test results from the camera prove that this is quite an effective way of monitoring your parked car. One day of testing yielded a lot of results. So we tested it by parking in the parking lot and just monitoring the traffic that went by and seeing how many cars would go by and if it would take a photograph of them, if they got really close to it, which it did. So all of the cars were photographed along with their license plate. So the time is printed and other pictures as well on the pictures, so the operator knows who and when the accident occurred. So the objective of this experiment was to construct a motion detection car security system that would be mounted on the windshield of a car, or it could be placed anywhere. Since it is very user-friendly, you could have it on your windshield, your dash, or any window that you would like to have it at. So we broke down the project into about 6 months. By December, we knew exactly what we wanted to build, which was this security camera for your car. So next I'll have my partners Lenford and Ryan come up and talk about the details.
Okay, so first look at the introduction. The name of this device is called the Motion Detection Car Security System. It is designed to be operated in cars and SUVs, and its basic function is utilizing a camera to capture pictures once motion is detected. The main technology used in this device is a PIR sensor. We'll now look at the PIR sensor circuit that we designed. Here's a 3D view of the circuit. With that said, we'll look at the basic operation of the PIR sensor. Now, the PIR sensor consists of three main elements. The PIR element, this detects infrared radiation emitted or reflected from objects. Once that radiation is detected, it is then sent to the amplifier circuit. This is where the amplifying is done. This increases the magnitude of the signal. Once that is done, we'll then send it to the comparator circuit. This is where the comparator circuit compares the amplified signal and determines if it should send it to the output. With that said, we'll look at the basic operation of the PNP and NPN transistor. Now these devices, they act as a switch. They operate in two modes. We have the saturation mode and the cutoff mode. The saturation mode is basically the on mode. Once it's above the 0.7 volts, it's going to reach the saturation mode and electricity will be flowing. Once it's below that, however, we'll enter the cutoff mode and no electricity will flow. So once we pass the transistor, we now go to the relay. The relay is connected as a normally open circuit. So once the PIR sensor detects a signal and sends it to the transistors, then it sends it to the relay, which as I said, the relay is normally open. So once it detects that signal, it will then close, and then it will send a signal to the camera, which will then take a picture. Now the supply voltage that we need for this circuit is 10 volts, and the trigger voltage is 0.5 volts. Like right here, this is where the camera will be connected, and once the relay is engaged, 0.5 volts will be sent to the camera and a picture will be taken. Now look at the device assembly. And now this is basically a front view of the device. As you can see, the PIR sensor is extruded through a small opening, and we use some glue to attach the enclosure to the actual camera. This is a rear view of the device. You can see this is the digital camera that we re-engineered, and this is the casing. Now this is the inside view of the circuit that we fabricated. And this is the outside board circuit. That's the PIR sensor, NPN transistor, PNP transistor, and 5 volts relay. With that said, we'll now move to the components.
So to continue on from where Lenford left off, we're going to start talking about the components on the board. We have stuff like the 547 transistor, a 557 transistor, unit cell relay, diode, and the PIR sensor. For the 547 transistor, it's an NPN BJT. In this setup, it is being used as primarily a switch. It feeds into the 557 transistor, which is a PNP BJT, which the 557 transistor is a general purpose transistor. Both of them are often used for gain or for being used as a switch. In this case, both of them are being used as a switch, which the 557 transistor feeds into the unit cell relay, which is a model 5K19F. It has a 5-volt coil, it's got 8 pins, and the other side that isn't the coil, those contacts are rated for 30 volts, 2 amps in DC. Why DC? Because that is what we are using. There are the ability to have 2 sets of contacts. We are only using one side of them, and we are only using the normally open part of the relay. So between the 557 transistor and the PIR sensor is the diode, the 1N4148. It is a silicon-based diode, and it's typically 0.7 volts. The manufacturer data gave a rating of 0.62 to 1 volt. And then finally, we have the PIR sensor itself, which is an onion IR. It operates between 2.7 to 12 volts. It is a low current PIR sensor. Usually it has an output of 0.1 milliamp, and it has a 100-degree cone for its sensor, meaning that it'll catch what's in front of it to a wide enough angle that you can put it out in front, and if something's going to impact it, it'll catch it as it comes in. It's not going to catch it too far out or too, it's not going to catch the car all the way out here driving by. It'll catch the car here driving by. So talking about that leads into the camera, which is a better the best digital camera. It is a 2.7-inch digital LCD display with a TFT or thin film transistor as part of the display. The camera itself had a 550 milliamp hour lithium-ion rechargeable battery that is built in. It also takes pictures at a resolution of 21 megapixels, which, for those who don't know, typically that size is about just shy of 5,000 by 4,000 resolution. Put that in perspective, a 720p 42-inch is usually 1366 by 768 pixels. So it's nearly 4 times the resolution of a 42-inch LCD display. The camera also has an external storage SD card. That is very useful to us for something like that. If a car, you take a picture, it gets stored onto the SD card. That way, to get access to a picture in case of a fender bender or someone vandalizing the car or something of that sort, you don't have to pull the camera out, pull everything out, and take it to your computer and plug it in and read the data that way. You can just pop out the SD card, go over to your computer, pop the SD card in, and take a look at the pictures. See what happened, where, what the triggers were, see the time, the date, all that fun information. That'll help you keep track of what's going on. So after that, we'll talk about a little bit of the design change from what the original design had for components to what it has become. So originally, the design that we found used a 7404 that was connected to the output of the PIR sensor. So the PIR sensor fed into 7404, which fed into a MOSFET. That MOSFET fed up and into the relay circuit. Originally, this required 2 separate voltage sources. The 12 volt, which was to be the car battery, and then it also needed an additional 5 volt source. This was going to be an issue unless we got additional circuitry to make a voltage regulator and regulate the voltage from the car down to 5 volts. Unless we picked some internal components of the car to sort of hijack their voltage. So we decided to change this idea and do some more research and find a simple design, which the simple design removed the MOSFET, the 7404, and the 2 separate power supplies, so I combined it all into one and just tossed in 2 transistors instead. It made it a much simpler design and easier to lay out in multiboard, as seen between the 2 pictures. The MOSFET is usually used in higher power systems, which with a 0.1 milliamp output, it seemed a little bit of a waste to use a MOSFET there. So that was one of the benefits. All the components, we go into the conclusion. So it's efficient. Something hits that sensor, triggers that sensor, it takes a picture. Something triggers the sensor, it takes a picture. Something triggers the sensor, it takes a picture. The battery life of the internal camera has many hours available to it for operation, because it only drains the internal battery is only used when it takes a picture, which means however many hours it would take to drain that battery is going to be taken up in fractions of seconds. So if it takes, if it took an hour, or 60 minutes in an hour, 60 seconds, 60 seconds in a minute, that's 3,600. If even at, like, let's say it takes 1 full second for it to take a picture, that's 3,600 photos that's going to go through before the camera dies. And we have to recharge it. It's another benefit. It's a rechargeable battery. And pretty much, for the most part, it's cost effective. Most of the pieces, besides the camera that was refurbished, are cheap. They're affordable. They're simple little components that, depending on how many you buy, sure, you buy 5, 10 of them. They're going to cost a couple dollars. Once you get into hundreds, possibly thousands, that usually, like, supplier cost goes down in, usually cents. Once this gets developed a little bit more, if we ever look into, building the camera circuit itself, that would also cut down on cost, because we once again bought a fully pre-built and functioning camera that was refurbished for the system. It makes it easier to work with initially, but further down the road, that $50 cost of the camera itself can sort of be worked down and negated by buying only the necessary pieces. So once again, it's a device that will watch your car for you, and you know it's going to work and it's going to last. Because once again, if 3,600 photos, if it dies in an hour of use, that could be days, that could be weeks, that could be months. It just depends on how active the area around you are. Sure, Christmas is probably going to be more active. It's going to die sooner. But on this campus, parked up in the upper lots like Orbis and stuff, not going to see much action. Camera could probably last the entire semester, if not more. I'll say multiple semesters. Thank you.